Hi everyone! In this video, I'll show you the solutions to the Class 6 homework problems. I hope you have all watched the Class 6 class video, as many of the important concepts like the GCD LCM, modular arithmetic, and Diophantine equations are covered in that class. And many of the techniques that we learned there will be used to solve these problems that we have for today. Let A, B, C, D be the ordered quadruple of not necessarily distinct integers, one of them in the set 0 to 1, 2, 3. For how many quadruples is it true that A times B minus B times C is odd? Okay, so how can we do this? So notice that the only possibility such that A times B minus B times C can be odd is if either AD is even and BC is odd, or we have AD is odd and BC is even. These are the two possibilities. Let's take the first possibility. So in how many ways can we have AD equal even? So the number of ways we can have two numbers A and D multiplied to even, well, we need to either have A odd, A can either be odd and D can be even, A can be even and D can be odd, or both of them can be even. And these are the only three possibilities. And note that if they're both odd, then the product will be odd, not even. Because in each of these three cases, the product of A and D is even. Okay, so how many ways is there to have A odd and D even? Well, there are two odd numbers, so two choices for A, and two even numbers, so two choices for D. So equal to 4 for this case. For the second case, we have, again, two choices for the even numbers, 0 or 2, and two choices for the odd numbers again. Same thing for the last case. There's two even numbers, so we do 2 times 2 equals 4. And they said not necessarily distinct, so we can have the same number. That's fine. So overall, we have 12 cases, 12 possibilities such that A times D is even. Now, what about B times C is odd? In order for B times C to be odd, both of the numbers have to be odd. That's the only case. So how many cases are there for this to happen? There's two choices for the odd number and two choices for the even number, giving us 4. So 4 cases, 4 ways for BC to be odd, and 12 for AD to be even. Overall, giving us 48 possibilities. Okay, now what about if AD is odd and BC is even? Notice that that's essentially the same case, because having AD even and BC odd is the same as having AD odd and BC even. So then we just do 48 times 2, so 48 plus 48, and that gives us an answer of 96 in total. So just to summarize the key steps, what we did is we looked at both the possibilities, AD even, BC odd, or AD odd, BC even. And then we found the number of ways for AD to be even by just making a table and seeing how many possibilities A and D could have, and the same thing for BC. And then we just multiply by 2 at the end since the cases are symmetric. Okay, so now let's take a look at our next problem. Which of the following expressions is never a prime number when P is a prime number? Okay, well, So first thing you might want to consider is that we have a bunch of square terms here, and the numbers are kind of small. So you might just want to start listing some out, see which of them was going to result in a prime number, because 4 of these choices will eventually lead a prime number. So maybe you can just try listing some possibilities out and seeing when they will reach a prime number. Okay, let's see the first possibility. So for p equals 2, this becomes 20. For p equals 3, it becomes 3 squared plus 16 equal to 25. For p equals 5, it's 5 squared plus 16 equal to 41. For p equals 7, it's 7 squared plus 16, which is just going to be equal to 65. But we didn't have to do that. We already see that 41 is a prime, meaning that it's not true that p squared plus 16 will never be a prime. Okay, now what? So this case is out, because it can be a prime sometimes. What about p squared plus 24? Let's try something similar. 2 squared plus 24 is 28. 3 squared plus 24 is 33. Sorry. I wrote equal to instead of plus. Okay, now 5 squared plus 24 equal to 49. 7 squared plus 49 is just going to be, 7 squared plus 24 is just going to be equal to, that's just going to be 50 plus 24 minus 173. 73 is prime, meaning that it's not going to be always true that p squared plus 24 is a prime number. It's never a prime number. So eliminate this too. Now C. Now this is where things get slightly tricky, okay? So let's just try a strange strategy. 2 squared plus 26 is 30. 3 squared plus 26 is 35. 5 squared plus 26 is just 51. And 7 squared plus 26 is just 50 plus 25, 75. 11 squared plus 26 is just going to be 147. Let's do one more just to see. 13 squared plus 26 is 169 plus 26, which is just 195. Okay, so this doesn't look like it's going anywhere. All these numbers are not prime. So maybe this one is the option choice. So the thing to notice here is that 51 is a multiple of 3. 75 is a multiple of 3. 147 is a multiple of 3. And 195 is a multiple of 3. Okay, well, if all of these choices are multiples of 3, maybe C is the answer. So maybe p squared plus 26 is always going to be multiple of 3. So that motivates us to consider p squared plus 26 mod 3. Okay, so what is p squared plus 26 mod 3? The answer is, well, here's a very special fact about a number squared. If p is a multiple of 3, then p squared is going to be 0 mod 3. So p is congruent to 0 mod 3. P squared will also be congruent to 0 mod 3. But if p is congruent to 1 or 2 mod 3, then p squared in each of these cases will always be equal to 1 mod 3. Because if p is 1 mod 3, then 1 squared is 1. So p squared is 1 mod 3. And if p is 2 mod 3, then 2 squared is 4. And 4 is the same as 1 mod 3. So no matter what, p squared will most of the time be 1 mod 3. And sometimes so basically from here we see that the only prime that's a multiple of 3 is 3. So p equals 3, then p squared is 0 mod 3. But if p is not equal to 3, then p squared is 1 mod 3. So clearly you can see that the first two cases are not prime, right? Okay, so the first two cases we know are not prime. So otherwise, if p is not equal to 3, if p is greater than 3, we can see that p squared will always be 1 mod 3. But notice that 26 leaves the remainder 2 divided by 3. So 26 is 2 mod 3, right? So for all primes greater than 3, p squared is 1 mod 3. And 26 is 2 mod 3. So their sum will be 3 mod 3 or 0 mod 3. So we can see that for all primes greater than 3, p squared plus 26 is a multiple of 3. And thus, it will never be prime. And we can check that manually that 2 and 3 don't work and are not prime either. So we can actually see that C is the answer. And the main hard step in this problem is realizing that these are all multiples of 3 and then seeing that, oh, now we can try proving it by taking mod 3. But you might not have seen that. And in which case, you could have just tried the possibilities, same thing for D and E, and you find that none of them work either. So then you could have also seen that C was the answer choice from there. So I'm just trying to give you all perspectives on how you could approach this. So to summarize, the idea was we see that A and B don't work. We see that C, we can see that all the choices are multiples of 3. And that motivates us to take mod 3 and see what patterns. Maybe we are having something that's always a multiple of 3. And then we can also check that D and E don't work manually, but I won't show you that here. Now let's take a look at the next problem. If P, Q, and R are prime such that P, Q, R 7 times P plus Q plus R, find P plus Q plus R. Okay. It's an interesting problem. So we have an equation P, Q, R equal to 7 times P plus Q plus R. So immediately we see the right-hand side is a multiple of 7, of course. So if the right-hand side is a multiple of 7, the left-hand side is also a multiple of 7. So then the left-hand side, well, what can it be? So if the right-hand side is a multiple of 7, one of P, Q, and R have to be equal to 7, since they're all prime. So let's just say that R is 7. Okay? So then we see that 7 times P times Q is equal to 7 times P plus Q plus 7, right? R is 7, we said. It doesn't really matter. You can also say P7 or Q7. They're symmetric. It's the same thing. Okay. Well, now we can cancel out 7 from both sides to get PQ equal to P plus Q plus 7. Or that PQ minus P minus Q is equal to 7. And from here, we can see that this looks a lot like Simon's favorite factoring trick. So what we can do is we can add 1 to both sides to get PQ minus P minus Q plus 1 equals 8. 7 plus 1 is 8. And then we can factor this using Simon's favorite factoring trick to get P minus 1 times Q minus 1 is just going to be equal to 8. And from here, let's check the possibilities. Well, we can either have 1, 8, 2, 4, 4, 2, 8, 1. But notice that P and Q are symmetric, So swapping them around won't really change anything. So these last two cases are just the same as the first two cases, essentially. They just have P and Q values swapped, and we don't really care what the individual P, Q, and R values. We anyways just want to find what P plus Q plus R. So it doesn't matter whether P is the value and Q is the other value, or we swap their values. So just the last two cases are just symmetric and they're essentially the same thing. So now we just check the first two cases. So if P minus 1 is 1, that would leave P equals Q, 2, and Q equals 9. If P minus 1 is 2, that would mean P equals 3 and Q equals 5. But the first case doesn't work, since that would mean Q is 9 and Q is 9 is not a prime. So that means we know that P is 3, Q is 5. Of course, the order doesn't matter. We can switch the order. But the 3 primes are 7, 3, and 5. So their sum is just going to be 3 plus 5 plus 7, which is 15. To summarize, we first saw that PQR has to be a multiple of 7, meaning that one of the primes is 7. Then we expand it out and see that this looks a lot like Simon's favorite factoring trick, and that gives us this equation here. And we just try the possibilities and find the value of P, Q, and R from there. So now let's take a look at the next problem. So this is one of the hardest problems in the homework for today. We have the GCD of A and B is 24, the GCD of B and C is 36, the GCD is C and D is 54, and this awkward condition. Okay, this is a lot. We have a bunch of GCD conditions we have no idea how to deal with yet. Okay, so let's look at each of the variables individually, because that would give us some insight into how to work with them for moving forward. So clearly, if the GCD of A and B is 24, A has to be a multiple of 24. Right? Because the GCD of a number is 24, then both factors have to have that factor of 24. So we know that A has to be a multiple of 24, and B has to also be a multiple of 24. But from the second condition, we know that B has to also be a multiple of 36. And then we know that C has to also be a multiple of 36. And then from this last condition, we know that C has to also be a multiple of 54, and D has to be a multiple of 54 too. Okay, so if B is a multiple of 24 and 36, it also just has to be a multiple of the LCM of 24 and 36. So let me just write this as LCM 24 and 36. And the LCM of 24 and 36 is just equal to 72. And similarly, if C is a multiple of 36 and 54, it has to be a multiple of the LCM of 36 and 54. Right? That's a very special property. And this means that it has to be a multiple of, well, 108. So A is a multiple of 24, B is 72, C of 108, D of 54. Now what? So now we've pretty much used all the conditions in some way. Really, this last condition is somewhat floating around here with no clue what we want to do with it. Okay. So now we really want to look at the GCD of DNA. Someone want to analyze that condition. A, we know has to be multiple of 24. D, we know has to be multiple of 56, 54. So the GCD of A and D has to be a multiple of the GCD of 24 and 54. So it has to be GCD of A and B will be a multiple of the GCD of 24 and 54, which is 6, because they both have factors of 6 in them, for sure. It could be more, but we know it has to be a multiple of 6. Okay, so we know the GCD has to be a multiple of 6. Now, what can we do? Well, we can see that the only multiples of 6 between 70 and 100 are 72, 78, 84, 90, and 96. So really, we've already eliminated down to only 5 possibilities, which is pretty good, right? But we can reduce it even more. So one way you can just try all these values. You can just be like, okay, 72, will it have these conditions satisfied? No. 78, will it have these conditions satisfied? Whatever, just keep trying them. And that's perfectly valid, and that will give you the correct answer. But we can be a little bit more clever and not have to work through all that computation meaninglessly. See, the reason that not all these possibilities work, so let me just demonstrate 72. So if 72 is a GCD of A and D, then we know that the GCD of A and D is 72, then they both have to have factors of 72 in them, which means that A would have to be a multiple of 72 as well. But if A is a multiple of 72 and B is a multiple of 72, then the GCD of A and B is now 72 and not 24. So hopefully it gives you an idea of why the cases don't work. the GCD has to be exactly 24, not multiple 24, exactly 24. The GCD has to be exactly 36 of B and C. So we can use a similar logic. So looking at the prime factorizations of 24 is 2 cubed times 3. 54 is 2 times 3 cubed. Of C is just going to be 2 squared times 3 cubed. And the 72 is 2 squared times 3 squared. Notice that, well, the GCD of A and B has to be exactly 24. So if A has more than one factor of 3 in it, if A has a factor of 3 squared in it, the GCD of A and B will then be 2 squared times 3 squared, not just 2, not 24. The GCD will be 72 instead. So we know that the factor of 3 in A has to be exactly 1. Exactly 1, no more. But the factor of 2 can be more than 3. It can be more than 3 if you want. It can be like 10 or whatever, because that won't matter. Similarly, for D, we know that the factor of 2 has to be exactly 1. But the factor of 3 can be 3 or more. Because if the factor of 2 in D was more than 2, then the GCD of C and D would now be 2 squared instead of just 2. And that would be contradicting our conditions. So now we can see that from only the factors of 2 and 3, if you look at only the factors of 2 and 3, the GCD of A and B is exactly 6. It cannot be a multiple of 6, but that's only the factors of 2 and 3. So the GCD of A and B we found to be 6, equal to 6. But that's looking at only the factors of 2 and 3. There's no reason we can't have other factors like 11 or 13 or whatever. And we actually do need a factor of 11, 13, or some other prime, such that to put it in this range, to make the GCD larger. So looking at our option choices, we see that 72 doesn't work, since 72 has more factors of 2s and 3s than just 6. 78, on the other hand, is just 6 times 13. So that does work, and that would result in A having an additional factor of 13, and D also having an additional factor of 13. So let's just check the other possibilities for completeness. 84 also has more factors of 2 and 3. 90 has more factors of 2 and 3 than just 1. 96 also has more factors of 2 and 3. So 78 is the only possibility, meaning that A and D both have to also have factors of 13. So 13 is the answer for this problem. And this problem was tricky for sure. But it mostly just boils down to looking at, A is a multiple of 24, B is a multiple of 72, C is a multiple of these prime factorization values. And then what we did is we saw that the GCD of A and D only had so few possibilities because A and D are both multiples of 6. And then from there we saw that looking at the prime factorizations, A has to have exactly one factor of 3, and D has to have exactly one factor of 2 in order for the GCD of C and D to be exactly 2 to the 1 times 3 cubed, and the GCD of A and B to be exactly 2 cubed times 3. And thus we saw that in order for the GCD of A and D to be from 70 to 100, had to have an additional factor of something like 13, for example, and you see that 13 does indeed work, and that's the answer for this problem. Now let's take a look at the last problem. Okay, so there's a prime number p such that 16p plus 1 is a cube of a positive integer. Find p. So let's just say that we have number x cubed equal to 16p plus 1. Okay? So if x cubed is equal to 16p plus 1, what does that mean? Well, okay, so what we notice is that this means x cubed minus 1 is 16p, of course, right? Makes sense. And if x cubed minus 1 is 16p, well, what does x cubed minus 1 remind us? Difference of cubes. So that you can factor this as x minus 1 times x squared plus x plus 1. And this is equal to 16p, right? So now what do we know? Well, we know that what we can immediately see is that x has to be odd, right? Because this right-hand side is odd, so x has to be odd, right? Makes sense? Okay, so if x is odd, then x minus 1 is even. And if x is odd, then if x minus 1 is even. And if x is odd, then x squared plus x plus 1 is going to be equal to an odd number plus an odd number plus 1, which is also going to be odd. So if x minus 1 will then be even, and this will be odd. Okay, so now we see that the right-hand side has a factor of 16 in it, meaning that since the right-hand side has a factor of 16 in it, the left-hand side also has a factor of 16 in it. But we see that x squared plus x plus 1 has to be odd, meaning that x minus 1 has to have a factor of 16 in it. So therefore, x minus 1 has to equal to 16. And then x squared plus x plus 1 will have to be p. Because x minus 1 cannot be, x squared plus x plus 1 cannot be an even number. Okay, so now, from here we can see that x has to be 17, right? Because x minus 1 is 16, meaning x is 17. So then we can see that 17 cubed is equal to 16p plus 1. Or that 17 cubed minus 1 is equal to 16p. And if you memorize their cubes, you would see that 17 cubed is just 4913. So 17 cubed is going to be 4913 minus 1 equal to 16p. And that would mean 4912 is 16p. Or p is equal to 307. And that's the answer for this problem. And to summarize the key steps, we first wrote our equation, our Diophantine equation, and then we rewrote it using difference of cubes formula, and then we saw parity. Parity is a very useful technique. We know some numbers have to be odd, some even, so we use parity to our advantage. We write this as even times odd, and then we see that x plus x plus 1 has to be odd, so x minus 1 has to be 16, and that means x is 17, or p is 307. So those are the main steps, and the insight really is that whenever you have variables that you don't know, just let it be a variable. It's going to make your life a lot easier. And always, again, be on the lookout for these factorizations, x cubed minus 1, difference of cubes, sum of difference of squares. They're going to be really helpful in all levels of problem. So thank you for watching this video. If you enjoyed it, be sure to subscribe to this channel in order to be notified of future math videos. Also, thank you for watching, and I hope to see you all next class.